Hi, my name is Tiagi, and in this video, I'll be going over the hyperbolic trig functions sinh x, cos x, and hyperbolic tangent of x. So to start, the first thing we notice about these hyperbolic trig functions is that they look pretty similar to regular trig functions. So let's start from there, right? If we imagine a regular trig function, we define it with unit circle, which is just a circle, x squared plus y squared, with radius 1, so it equals 1. So the circle looks something like this. And to define it, right, we use an angle. So we have an angle theta, okay? And if we want to consider what this angle theta means in terms of trig functions, right? Cosine theta is equal to the adjacent of the hypotenuse, or in other words, it equals x, right? Because the hypotenuse is 1. So cosine theta is our x value. Similarly, sine of theta in the unit circle is our y value, because it equals the opposite, which is our y value, divided by the hypotenuse, which is 1. Okay? And with that formula, right, we can see that a trig identity holds, right? Sine squared theta plus cosine squared theta is equal to 1, right? So that identity holds. There's also one thing you might have known about the trig function, or sorry, by the trig functions, is that the area right here, right, let's call this area of the sector, A of S, right? We know the area of sector is going to equal the proportion of the angle, right? So theta over 2 pi, how much of the total circle are we looking at, times the area of the circle, right? And the area of a circle is equal to pi r squared. The radius is 1, so the area of the sector is equal to theta divided by 2 pi times pi, or in other words, the area of the sector is equal to theta over 2. So in other words, this area of the sector that we make when we use an angle theta is equal to theta over 2. So what this means is that area and theta are proportional, right? So if we increase our theta, we increase our area by a predictable amount, by 2. Okay? So that's the relationship we have with regular trig functions. But for hyperbolic trig function, right, the way we define it is with a hyperbola, which is just like a cone, the conic section, if we cut it such that we have this section and this section there. In other words, better explanation, right? X squared minus y squared equals 1. That's a hyperbola, right? And it looks something like this. Okay? And we're going to have the x-intercept at 1, x-intercept at -1. Okay? And for hyperbolic trig functions, right, we only define it when x is greater or equal to 1. So this part is kind of not being looked at when we're defining it, okay? And similarly, right, we're going to draw a line, right, and our value here. And our value here is going to be equal to cos, right? So our x value is going to be cos something, right, the input. So in this case, instead of inputting an angle, right, we're not inputting this angle here. What we're doing is we're inputting the area. We're inputting this area here. So in hyperbolic trig functions, we input something called a hyperbolic angle, which is actually not really an angle in the way we think of it, right, with a circle. It's actually better to think of it like kind of like an area, right? So this hyperbolic angle, consider the area between here to the point and between the hyperbolic function. So this is our hyperbolic angle, right? And so what we're doing is we're plugging in this hyperbolic angle, right? And this hyperbolic angle, we're plugging in 2 times the area, so that's our hyperbolic angle. Similarly, for sine, right, we're going to do sine or sinh x, and that's how we define the hyperbolic trig functions geometrically. So it's this area underneath is the input for the hyperbolic trig function, or the hyperbolic angle, right? That's what it's defined as. And some things to note with this, right? We can also do an identity here. We can plug in cosine and sine or sinh, right? So cosine or cos squared x minus sinh squared x is equal to 1. So we have our Pythagorean identity for hyperbolic functions. And we also have the idea, right? In this case, we said the area is proportional to theta. But here we can see clearly it isn't, right? Because we can't really relate this area here in the angle theta. So area is not proportional to theta, which also means that our angle, too, isn't really proportional. The hyperbolic angle, right? X isn't proportional to our theta as well. So x, sorry, is not proportional to our theta, right? Because x, right, this angle that we're putting in does not equal this angle here, right? We're not plugging in the angle here, we're plugging in the area, so it's not, x is not equal to theta, right? One other thing to note is that as theta approaches pi over 4, right? So as we get closer to pi over 4, we're getting our area closer to infinity because the function, right, x squared minus y squared equals 1, there's an asymptote, a asymptote like that. And so as we approach this closer and closer, right, we're going to reach a point, if we go to infinity, where the area just keeps going. We don't ever touch it, and so we reach infinity. So theta keeps going to pi over 4, and then the area approaches infinity. Okay, so that's kind of a visual way of looking at it. Now let's look at the actual functions individually. Right now we have this baseline set up in our minds. So first we have sine, or sinh, of x. And the formula for this is e to the x minus e to the negative x divided by 2. In other words, e to the x divided by 2 minus e to the negative x divided by 2. So graphically, right, if you imagine what the graph would look like, we're going to have a e to the x divided by 2 term. So it's going to look something like this. And we're going to have a e to the negative x over 2, which looks like that, flipped over the x-axis because we have negative sign. So it's going to look something like that. And so if we combine those two, right, so we add them together, our hyperbolic trig function, sinh of x, is going to look something like this. Right, and so this is what our hyperbolic trig function looks like. Okay, and from this we can see our domain is going to be negative infinity to infinity. Our range is also negative infinity to infinity, which should make some sense graphically too, right? Because our area can go all the way to infinity, right? Because we can just keep making the angle bigger and bigger. And our sine can also go to infinity too, right? So it can go all the way there, and it can also go to negative infinity, right? Because it can go negative if our area is negative underneath the graph. Okay, cosine or cosh of x, this one's equal to e to the x plus e to the negative x divided by 2. Right, so graphically, we're going to look at something like this. So e to the x is this way, e to the negative x is this way. And so cosh of x, if we add them together, is going to be something like this. Right, and we're going to stop right there. So if we plug in 0 and 0, right, we get 1 plus 1 is 2. 2 divided by 2 is 1. So from there, so 1 all the way up. So domain, again, is negative infinity to infinity, because we can have negative areas, right? They can go all the way to infinity. And our range, this time, is going to be from 1 inclusive, right? Because we can have 0 to infinity. Which should make some sense graphically, right? Because if you look at our graph, right, cosine of x, the smallest value, right, it reaches is here, 1. Right? The cosh, it goes from 1 all the way to infinity. So that's the slowest value, smallest value reaches. And finally, we have hyperbolic tangent of x. And this is defined as sine or sinh of x divided by cosh of x. Or in other words, right, it would be e to the x minus e to the negative x divided by e to the x plus e to the negative x. So this one's a little hard to graph and just like kind of reason it out. But if we look at our function, right, tangent is going to be the slope, right, sine divided by cosine. And so we can see that our slope is going to reach, y equals x, right? It's going to keep increasing to theta over pi over 4, right? And once we reach theta over pi over 4, our slope is 1. So our max output is 1. Our min output is also negative 1, right? Because our slope, we have another asymptote this way, right? So our min output is negative 1. This means that our function is going to look something like this, right? And also another thing to note is that we have an infinite amount of values or inputs in between, right? So again, max value is going to be 1, min value is going to be negative 1. We do have a slope of 0 if we reach here, and so just connecting the dots, right? We're going to go something like this. Right, so that's our hyperbolic tangent of x. And again, the reason why is because we're going to have from negative 1 to 1, and there's going to be an infinite amount of slopes in between and inputs in between as well. So our domain is negative infinity to infinity, and our range is negative 1 to 1 inclusive. And that's all of the hyperbolic trig functions. Okay? And an important thing to note is that for all these hyperbolic trig functions, right? Let me just erase it all. A lot of properties we have with trig still stand, and a lot of the things we do with trig still stand, even though, as we can see, they're not exactly the same, right? Trig uses regular angles, hyperbolic trig uses hyperbolic angles, or like areas, right? So it's a little different, but there are some similarities, and similarities include things like reciprocals, right, they still exist. So, you know, secant, hyperbolic secant of x is going to equal 1 over cosh of x. Same thing there, right? So for all of those still exist. Inverses exist too, so you can have, right, inverse cosh of x. Identities too, a lot of them are pretty similar. Right, we saw that the Pythagorean identity was pretty similar. We also have identities like, sinh of x, sinh of negative x is equal to negative sinh of x, right, which should make some sense visually. You can do that on your own. Derivatives also kind of are pretty similar as well between trig and hyperbolic trig. So some derivatives, right, sinh of x is equal to cosh of x for derivatives. Derivative of cosh of x is equal to sinh of x. So a little difference there, right? It doesn't equal negative, it equals positive. And derivative of hyperbolic tangent is equal to secant, hyperbolic secant, square root of x. Okay? And just a quick note on the application of this, right? This really applies to physics. It applies to things like math if you're solving differential equations. And in physics, it applies to a lot of fields, right? It applies to things like catenary curves, which are like hanging chains, and things like special relativity for things like rigidity. Okay? And yeah, that's everything you need to know, or the basics of hyperbolic trig functions. Thank you all for watching, and I'll see you guys all tomorrow. Bye.